Assalamualaikum and good morning for my teacher and our classmates. Today I want to presentation my assignment. The title is Integration of Solar Energy in Urban Infrastructure. My name is Muhammad Fakhar Rizi bin Muhammad Fauzi. Introduction. The integration of solar energy in urban infrastructure is the process of embedding solar technologies into the everyday framework of cities covering residential, commercial and public space. These include solar rooftop on building, solar carport, solar powered street light with the integrated photovoltaic, BIPV, smart grid, and even solar powered public transport system. Instead of treating solar energy as an add-on, it becomes the core element of city planning and development. Urban infrastructure is increasingly designed to generate clean energy on site, reducing depends on centralized fossil fuel power plants. Why it is important? Why it matters today? In recent years, global challenges such as change design, increasing fossil fuel costs, urban population growth, and the push for net zero target that make solar energy integration crucial. Between many nations, including Russia, the EU, the US, and China, have introduced incentives and policies to accelerate renewable adoption. At the same time, the cost of solar PV modules has declined significantly, making it one of the most affordable energy sources. Urban centers, which consume the majority of the wood energy, are at the forefront of this transition. Integrating solar energy not only support sustainability goals but also strengthens energy resilience, reduce carbon footprint, and create green job opportunities, aligning with global agendas like the UN Sustainable Development Goals. The issues and its elaboration with fact and views. This table for integration of solar energy urban 2021 to 2025. The elaboration. 1. Global push for renewable energy. Growing concern about climate change have driven countries worldwide to explore sustainable energy solutions. Many urban areas are now aligning with the UN's Sustainable Development Goals, especially Goal 7, affordable and clean energy. Governments are increasingly incentivizing solar projects as part of national climate policies. Urban challenges and opportunities. High population density in cities lead to greater energy demand, but also limited available space for solar installation. Innovation solutions like solar rooftop, building integrated photovoltaics, and floating solar are helping overcome spatial challenges. City can serve as testing ground for cutting-edge solar technology due to their infrastructure diversity. Leading cities and regions. Cities like San Diego, Tokyo, and Amsterdam are integrating solar into public grid, transportation system, and smart grids. In countries like Germany and Austria, solar energy forms a significant part of urban infrastructure today. Some urban zones have even mounted solar panels on new buildings, accelerating adoption. Patterns and technology trends. Rooftop solar remains the most common method of urban integration, offering localized energy production and global grid balance. Emerging trends include solar canopies over parking lots and solar powered street lighting. The problem issues. While solar energy offers great potential for sustainable urban development, several significant challenges hinders its widespread adoption in cities. This issue must be addressed to fully harness solar power in urban infrastructure. 1. High initial cost. The upfront expense of purchasing and installing solar panel and related equipment is often a major barrier, especially for smaller business and residential buildings. 2. Limited space and structural constraints. Urban areas have limited rooftop and land space for solar installation, and older buildings may not support additional weight of structure modification. Nearly tall building or trees can cause shading, reducing solar panel efficiency. 3. Regulatory and policy barriers. Lengthy and complex permitting process along with inconsistent regulation create delay and discourage investment. Some cities lack clear policies and incentives promotion solar energy adoption. 4. Technical and maintenance challenge. Integration with existing urban electricity grids requires specialized knowledge and technologies. Maintenance can be costly and complicated in dense urban environments. 5. Public awareness and engagement. Many urban residents and decision makers have limited understanding of solar technology benefits and costs. The effects. Environmental effect. 1. Reduction in air pollution. Solar power system reduce reliance on fossil fuel-based electricity, cutting emissions from power plants and vehicles. 2. Lower greenhouse gas emissions. Solar integration significantly reduce CO2 output, especially when used to power electric vehicles and buildings in urban areas. 3. Sustainable urban development. Utilizing rooftop parking lot and other existing structure for solar panels minimize land use impact and support eco-friendly city planning. 4. Mitigate noise pollution. Solar energy systems operate silently, contributing to quieter, more more livable urban environment. Energy and infrastructure effects. 1. Decentralized battery generation. Rooftop solar panel, solar carports and building integrated photovoltaics. And it enables cities to produce electricity close to where it consumed. 2. Grid stability and challenge. Variable solar output can lead to grid economies effects. 1. Capital investment and economic growth. Solar infrastructure requires upfront investment in technology, installation and grid integration. 2. Job creation and workforce development. High demand for skilled labor. Solar panel installer, engineer, electrician. 3. Grid infrastructure cost optimization. Distributed solar reduce the need for large scale grid upgrades and new power plants. Social and technology effect. 1. Technology enables social inclusion. IoT enable community solar projects allow broader participation and democratize access to clean energy. 2. Education and awareness powered by technology. Smart display and apps inform citizens about their energy use and environmental impact, encouraging sustainable living. Empowered community via technology. The advantage and disadvantage. The advantage. 1. Reduce in energy cost. Solar powered reduce electricity bills for household, business and public facilities. City save on energy expenses, free fund for other services. 2. Environment benefit. Decrease greenhouse gas emission and air pollution. Help city meet climate goal and improve urban air quality. Energy independence and security. Reduce reliance on fossil fuels and imported energy. Distributed solar system increase resilience against grid pressure and blackout. 4. Job creation and economic growth. Generate employment opportunities in installation, maintenance, manufacturing, and R&D. Stimulate local economies and support green industry. 5. Optimize use of urban space. It is rooftop, vacant parking lots, and other good development without requiring additional land. The disadvantage. 1. High initial cost. Installation of solar panel, inverter and supporting infrastructure requires significant upfront investment. Although price has dropped, initial capital can still be a barrier, especially for low-income households or small business. 2. Intermittency and variability. Solar power generation depends on sunlight with various by time of day, weather and season. Requires energy storage system or backup power source to ensure reliability. 3. Space limitation. Urban area may have unlimited rooftop or open space suitable for solar installation. Shading from neighboring buildings or trees can reduce solar panel efficiency. 4. Grid integration challenge. Distributed solar installation requires smart grid technology and updated infrastructure for stable energy management. Existing grids may need costly upgrade to wind power flow and variable input. 5. Maintenance and lifespan. Solar panel require regular cleaning and maintenance to operate efficiently. Panel degrade over time, typically 25 to 30 years lifespan, requiring replacement and disposal solution. 6. Aesthetic and horticultural concerns. Solar installation can often the appearance of buildings or storage area. Visual impact may cause resistance for residents of present. The consequence. The positive consequence. 1. Environmental improvement. Significant reduction in greenhouse gas emissions. Lower air pollution, improve urban air quality and public health. 2. Economic benefit. Reduce energy costs for household, business and government. Job creation in solar installation, maintenance, manufacturing and related sector. Increases property value for building equipment with solar system. 3. Energy security and reliability. Diversifies energy source, reducing dependence on fossil fuels and imports. Distribute solar system enhance grid resilience and reduce outage risk. 4. Solar augmentation. Improved quality of light flow, cleaner air and sustainable energy access. Increase energy access for low-income communities via community solar projects. Strengthen community engagement and empowerment through cooperative ownership models. 5. Technology progress. Driver innovation in solar technology, energy storage and smart grid integration. Facilitates the development of smart city with efficient energy management. The negative consequence. 1. High upfront cost. Solar installation involves significant initial investment, which may be a barrier for some individuals, business, and municipalities. 2. Intermittency and availability issues. Solar energy production depends on sunlight availability, only days and nighttime reduce generation. Requires complementary energy storage or backup system, increasing complexity and cost. Space and site limitation. Limited rooftop space or shading from surrounding buildings can reduce solar panel effectiveness. Not all urban structure are suitable for solar integration. 4. Grid management challenge. Existing electrical grid may require an upgrade to handle distributed solar power, managing relevant input and two-way electricity flow at technical complexity. 5. Maintenance and life cycle issues. Solar panels degrade over time and require maintenance to sustain performance. End of life disposal and recycling environment and logistic challenges. How to overcome? 1. To reduce high initial cost. Government incentive, subsidies, tax credit, rebate, and low interest loans to lower upfront expenses. Innovation, financing, solar energy, power purchase agreements, and community solar model to split costs. But purchasing programs. City or cooperative buy equipment in volume for discount. Address intermittency and durability. Energy storage. Invest in battery system. Lithium-ion flow battery to store excess solar energy for nighttime or cloudy days. Grid modernization. Develop smart grid and demand response program to balance supply and demand. Hybrid system combine solar with other renewables or conventional sources for stable energy. 3. Maximize space and system integration. Building integration photovoltaics incorporate solar panel into window, facade, and other surfaces. Innovation design. Use vertical solar panel, solar canopies over parking lot and public space. Shading analysis. Use technology to identify optimal placement to minimize shading risks. 4. Upgrade grid infrastructure. Smart grid technologies implement advanced sensor, automation, and communication system to manage distribute generation. Policy and regulation. Update standards to support overflow and distribute energy to solve. 5. Ensure maintenance and life cycle management. Regular maintenance program. Set schedules and protocols for cleaning and servicing practice. Recycling and disposal. Develop robust recycling facilities and regulation for end-of-life solar panels. Research on durable materials. Invest in R&D for testing eco-friendly solar components. 6. Address aesthetic and social concerns. Community engagement involve local stakeholders ready to address concerns and preferences. Design integration. Work with architect to create visually appealing solar installation. Pilot project. Demonstrate benefit with small scale visible projects to building public support. 7. Mitigate government impact of manufacturing. Green manufacturing. Encourage production using renewable energy and environmentally friendly materials. Circular and economy. Promoted panel use, refurbishment, and recycling. Supply chain transparency. Ensure ethical sourcing of raw materials. Conclusion. Integrating solar energy into urban infrastructure offer significant benefit, including reduced energy costs, lower environment impact, enhanced energy security, economic growth, and improved public health. It also drives technological innovation and supports the development of smart, sustainable cities. However, challenges such as high upfront costs, intermittency, space limitation, with integration complexity, and social acceptance must be addressed to fully realize this benefit. Overcoming these obstacles requires coordinated effort through supportive policies, advanced technologies like energy storage and smart grid, community engagement and investment in education and local manufacturing. By embracing these strategies, the city can accelerate the transition quickly to reliable and equitable energy system, contributing meaningfully to climate goals and improving the quality of urban life for all residents. This reference in session. Thank you for lending your ears. Do you have any question? Yes, ma'am.
Assalamualaikum. My name is Fahmi. I want to ask a question. What is solar energy integration into urban infrastructure?
Using solar power in city system like building, street light, and transport. Any question?
Assalamualaikum and good morning. My name is Muhammad Alaika. My question is what are the challenges?
Thank you, Haika. This answer is high cost, interspace, shading from tall buildings, and storage needs. Last question. Okay, thanks for your question. My answer is lower bills, clean air, job creation, and less dependence on fossil fuels. Thank you all to hear my assignment presentation. Thank you too for teacher. Thanks.
Okay, class.